Hey, good afternoon from the beautiful city of Boston, and good morning and good evening to anyone else. My name is Bishoy Galoaa. I'm an incoming PhD student in Northeastern University. I work under the supervision of Professor Sarah Ostadabbas. I work mainly in visual perception and tracking problems. In, and mainly today, we're not going to talk exactly or specifically on our work for VAGV, but instead our research direction and how we think that the state-of-the-art methods are not are not did not achieve everything, and we are trying to rethink the boundaries of the state-of-the-art trackers or research directions. So why do you want to do this? Our idea is that we want to solve these problems, like different problems that we have in our industry or day-to-day life. Like, for example, follow a child through busy daycare, or even when it's out in the crib, track a pedestrian through a complex scene, or distinguish athletes on the same team. But and how also learn from just few examples, because we work on small data sets, which is a big problem that sometimes get neglected. Everyone keeps talking about large scale data set or big data sets. So starting on that, why these challenges are still persistent and why the state-of-the-art methods did not solve them, and why are we here? So, for example, the simplest problem that we have and we need to fix is, for example, occlusions. Occlusions are when two subjects are behind each other, cross path, or have some complex scenario or complex path happening. And a human visual system can track through occlusion easily without even thinking. We can estimate who's being occluded and who's being disoccluded or being like in front of the subject. And for example, in this figure, we can see in between the three frames, like they're not like sequentially next to each other, but they are like, I think it's like 10 seconds of video. We can see that like these subjects either switched IDs or get fragmented IDs or lost the tracking altogether. And we can see different types of tracker. ByTrack is like a really established state-of-the-art tracker. DragonTrack is our VAGV work. And of course, this is the error happening to ByTrack. Another example are simply ID switches, is when two subjects are mostly like similar in appearance or similar in motion, and they would switch the IDs together. So one would take the other's ID. And of course, similar appearances is when we try to distinguish between extremely visually similar objects. For example, in that example, we have a triplets wearing the same clothes. So it's hard for any tracker or like any not fine-tuned tracker to keep track of the IDs of the different subjects. So, and also, of course, sports teams that would wear the same uniform. And we also have the crowding scenes. So complex interaction between multiple objects are computationally demanding, especially if we're doing some detection, tracking by detection. That means that the model needs to update its detection and its re-identification every frame, which can be computationally heavy. So of course, the dense crowd create frequent occlusions. And we have the small data domains. So we have limited training example, for example, like the infants in a crib, which can be really hard to collect and it's under high privacy. So these methods need to learn from sparse data. So now we listed all the challenges, but how and why these state-of-the-art never were able to solve these, as we've seen in a couple of examples. So for example, between 2016 and 2018, we have the SORT, which is the simple online real-time tracking algorithm. And then we got Deep Sort that integrated the appearance features. And then these methods struggled with occlusion and similar appearances because they never tried to model this problem. And in the transformer, then in 2021, in the transformer-based methods, we got Trackformer, we got Motor, and we got TransTrack, which added the end-to-end learning, and they had better context understanding, but there was always room for improvement. And as we can see in the figure, although the accuracy, which is MOTA, which is the multiple object tracking accuracy, was increasing, but also we were getting lower frame rates. And before starting listing our work and our research direction, I would love to go through the key evaluation metrics. We have the most famous and the most well used or used by everyone is the HOTA, which is the higher order tracking accuracy that try to balance between the detection and the association. And we have the MOTA, which is the multiple object tracking accuracy, which focuses more on the detection errors. And finally, we have the IDF1, which is the same as an F1 score that try to balance between the true positives and the true negatives and the false positives and the false negatives. And it always tries to identify the consistency throughout the tracking. So it's as if trying to say, oh, I was able to identify subject one throughout n number of frames throughout the sequence. So let's go through a big overview or a big picture of what we're trying to do. Again, as we listed the major barriers to a robust tracking or a state-of-the-art tracking, we're trying essentially in the grand scheme of stuff, we're trying to extend human perception. Because what is the state-of-the-art at the end of the day? It's just a human trying to track stuff. So I think this is why we always try to look on how humans are able to easily track, perceive, and see anything around them. So we have DragonTrack, which is our work in VAGV, and then we have Moti, and then we have UniTrack. So every piece of this research tried to tackle a specific theme or a specific problem. So let's go ahead and try to talk about DragonTrack. So DragonTrack was the first step that we tried to model and to overcome the existing state-of-the-art methods. So DragonTrack was a transformer-enhanced graphical tracking that addresses occlusion and ID switches. And it utilizes, as we can see in the figure, it utilizes a DETER, which is like an object detector, a transformer-based object detector, to get both things, to get the initial detections, which are just bounding boxes. And then we have the feature that we extracted them from the encoder inside. So from the bounding boxes, we get the appearance features. From the bounding boxes, we get the geometric features, and we get a novelty or a contribution that we added, which are the positional features. So we try to model the motion or the displacement of each bounding box. And lastly, from the encoder, we get the extracted feature. And then we utilize an MLP to project these embeddings and then concatenate them all together to have a concatenated embedding that we then try to train a graph convolution network using a contrastive loss between pairs in order to construct the embeddings of the detected subjects. And then we extend this to have the cosine similarity between subjects, and then we added a learnable sinkhorn normalization. So in the end, we get a Hungarian association or a track management, which is the last piece of the algorithm. And then we can get the tracking. So this was an end-to-end. The main challenges that we had in this work is how to be able to construct either the contrastive pairs, because we only used hard negatives and hard positives between the pairs. So for the hard negatives, it was easy to construct. We got the subject from different sequences or really far frames. So this was easy to do. And for the positive pairs, because we are using the MOT17 and the MOT20 data sets, so they provide us with the ground truth, though it was easy to pair them together using the IDs. So this combines the transformer detection with the graph modeling all together. So this was a really good starting point for our problems because it helped us solve a lot of stuff. Because using this end-to-end learning, we could have adapted to any other tracking problem. So for example, in this visual example, we have more consistent tracking throughout occlusion, as you can see, and it helps us build a really good tracker from an end-to-end algorithm. For the results, we compared DragonTrack against both state-of-the-art CNN-based and transformer-based methods on the MOT17 and the dense track. And as you can see, we achieved higher accuracies both on the HOTA and the MOTA and the IDF1, but we still lacked from state-of-the-art ID switches. So the next piece of our research direction, which called Moti, stands for More Than Meets the Eye, which is based on an optical flow-based tracking that maintains tracking during even prolonged occlusion. In its core, it uses a softmax platting for the disocclusion features. This work just got accepted in ICML 2025. So here we can see how Moti sees the world. So Moti processes the video frames on the left, estimate the optical flow from the middle, and then generate the disocclusion matrices on the right to track objects throughout the occlusion events. So the optical estimation helps us to compute the dense motion fields between frames to model the object movement, even when partially or fully occluded. And then we use the softmax platting that traps the feature along the flow vector to create a disocclusion-aware representation, as we saw in the video before. And then we introduced a module called ETEM, which it stands for the Enhanced Track Embedding module, that takes as an input, takes the query features that we got from the detector, and then we use the position and the splatted motion features, and then we use a multi-head attention to fuse the temporal and the appearance information, and then finally it applies a linear projection and a feed-forward layer for robust embedding updates, and then it outputs the enhanced track queries with improved identity continuity. So in the prolonged occlusion, we can see, for example, in this example, subject 3 and 8 undergo prolonged occlusion from subject 1, 4, and 6, and the model loses track. But Moti keep tracks of subject 5 and 1 without any ID switches throughout the prolonged occlusion duration. Also, for the heavy crowded scene with multiple different occlusions throughout the scene, we see that Moti was able to estimate and keep track of each subject under either occlusion from another moving object or a static object like this light pole. And even if Moti loses track of a subject, it regains it after the occlusion. And for sports, Moti was able to perform really well on like heavily similar subject and partial occlusion, not prolonged occlusion, but partial occlusion throughout. You can see different sequences of the sports Moti. And then, of course, for the more detailed visual results, we can see that ID10 go through partial and prolonged occlusion throughout the sequence, but using the disocclusion matrices and the optical flow, we maintain tracking throughout the whole sequence. Again, for the results, we evaluated Moti on Moti 15, 17, and 20, and dance track, and also sports Moti, showing state-of-the-art metrics throughout all the data sets. Last but not least, we have UniTrack, which is still undergoing research that we have in our lab. That is a unified loss function for tracking optimization with a graph-based differentiable loss. This piece of research, in my opinion, is the most interesting one because it transforms the whole problem into a model agnostic. Without optimizing the model architecture or the training or the fine-tuning, just updating the loss function that we use, because I think throughout the whole state-of-the-art method, no one tried to tackle on the loss function used. So we try to make a unified loss function that optimizes the tracker in an end-to-end way. So we use this graph definition that represents the tracking scene into nodes representing tracked object at time t, and then the edges are encoding the spatial and temporal relationships, and the edge weights are derived from the learned flow variables. And then we try in this research to identify 3 types of errors and try to tackle them. So we have the type 2 error with our drift, that sometimes these trackers just lose tracks with time. And we have the similar subject with this type 2. And then we try to make sure that even the simple types of errors, such as the ID switches, are also tackled in this unified loss formulations. As of the results, UniTrack was tested over 3 different trackers, motor, trackformer, and fair MOT, which are two of them are end-to-end transformer-based, and the other one is tracking by detection. And we also try to utilize two datasets that are the MOT17 and the MOT20. And throughout this experimentation, we've seen that the unitrack-based models that were trained and validated on these datasets achieved higher metrics. As for the visual results, we can see easily that any unitrack trained model will be able to avoid the errors that the previous models were able to miss. So for example, here we can see subject 90 being fragmented and getting a new ID. In our case, we maintain the ID even after the occlusion or the complex scene. And on the bottom, we can see that subject 49 also gets a new subject after a while. But in our case, we maintain it even after and before the occlusion. Of course, all this talk about state of the art is not for academia only, but it's also utilized for our real world application. For example, we use these trackers for infant tracking, sleep monitoring, car pedestrian interactions, or complex scenes. And as we've seen, like the sports MOT analysis, and they have a real world application. Of course, we have solved some problems, but still we have remaining problems. We were able to achieve occlusion handling and prolonged occlusion handling. We were able to use these trackers for crowded scene robustness and temporal drift reduction, and also to present and introduce a plug-and-play optimization and to have a model-agnostic solution, such as the unitrack solution. The remaining one, even though these models have state-of-the-art metrics, but the number of ID switches is still relatively high. We would love to have or solve the long-term temporal memory to try to deploy these trackers on long-term memory. And of course, the extreme appearance similarity, like the triplets and the sports MOT, would love to even improve it more. And of course, the data scarcity adaptability, where we would love to utilize these trackers and this research direction on small data sets domains. And last, I would love, because this work is a collaboration between many people in our EC lab, so I'd love to thank them. And I'm open for questions. Thank you.
All right, so at this moment, I don't see any questions. There was a general question that asked if the event is being recorded. Yes, it is. And the reminder here is that look in your inbox tomorrow for a link to all of the playbacks of the presentations that were given today. Plus, especially for this talk, there's a lot of follow-up papers. I try to post a few of them there in the chat, but we'll gather up all the links to the papers and include those as well. We do have a question that came in. Let's read it in real time. The edges of tracking encode spatial and temporal features of the tracked objects, vertices. Can you give examples of the spatial and temporal features in the edges?
Yes. So again, that's a really good question. And we modeled the whole tracking scene in the way that you can see in this graph component. So for example, you can see at T and T1, T+1 and T+2, we can see these are the temporal, imagine if these are the subject that being tracked, and these are the vertices and the edges and the weights. So this is an example that we can model the graph on it. So if I understand the question correctly, the green lines are the spatial edges. So this is, for example, how far two objects are from each other, or how much the displacement between different frames. And the flow weights are how we encode the confidence. So this is the confidence encoding in the continuity. So yeah, I think we utilize these edges and these spatial edges to model a tracking scene.